Hi everyone. Today we have discussed about the derivation of electrostatic boundary conditions in the electric field. The solution of Poisson's and Laplace equations should always satisfy certain conditions at the boundaries between the different media in the electric field. So these conditions pertaining to normal component of the displacement and tangential of the electric field intensity and refraction lines of force are called boundary conditions. The statement of boundary conditions are tangential component of electric field E is continuous at the surface, that is E is same just outside the surface as it just inside the surface. The normal component of electric flux density is continuous if there is no surface charge density. Otherwise, D is discontinuous by an amount of equal to the surface charge density. Consider a interface or a boundary between two dielectric constant, that is epsilon 1 and epsilon 1 in the electric field. So this is the basic diagram we have to follow with that for deriving the boundary conditions. This is a dielectric medium 1. So this is a dielectric medium 1. So we have a epsilon 1 for dielectric medium 1 and epsilon 2 for dielectric medium 2. So we have to calculate the distance in del x, del y for horizontal and vertical respectively. So we have to represent the normal component in the horizontal and tangential component in the vertical. So this figure shows the boundary surface between two dielectric media. Consider a rectangle of length del y and width del x at the boundary of two dielectric media as shown in figure. So in electrostatic field, the voltage around any closed path must be 0. That is V equal to closed integral of E dot dl equal to 0. So applied to this rectangular path in this diagram ABCDE, in which AB is just inside the medium 1 and CD is just inside the medium 2. So as shown in figure, closed integral of E dot dl equal to E t1 del y plus E n1 del x minus E t2 del y minus E n2 del x, where Et1 and Et2 are the average tangential components of E along the path AB and CD, and En1 and En2 are the average normal component of electric field along the path BC and AD. So as the sides AB and CD are brought close together, the length BC and AD approaches is 0. So that's why del x equal to 0. So this condition is applied to an above equations. We have obtained with that Et1 del y minus Et2 del y equal to closed integral of E dot dl equal to 0. So from this we can derive with that. So the del y is a common, we have to bring into an outside del y into Et1 minus Et2 equal to 0. From this Et1 equal to E2. So therefore the tangential component E is continuous at the boundary. So for second consideration, consider a pillbox at the boundary of two dielectric constant epsilon 1 and epsilon 2 in an electric field, and it is assumed that there is no free charge on the boundary surface as shown in figure. So that is a epsilon 1 and epsilon 2, then we have a dn1 and dn2. So this considers a pillbox is separated into a two component. So apply Gauss law to the pillbox at the boundary. Since there are no charge enclosed by the pillbox, so the surface integral of electric flux density over the pillbox surface is 0. So from that, surface integral of dn1 into ds minus dn2 into ds equal to 0, where dn1 is the electric flux density in the medium 1 and dn2 is an electric flux density in the medium 2, where ds is the surface area of pillbox. So from these equations we have obtained with the dn1 equal to dn2. So the normal component of electric displacement or flux density are the continuous across the boundary between two media, if that is they are equal. If the charges are enclosed by the pillbox, the surface integral of electric flux displacement over the pillbox surface is surface integral of dn1 ds minus dn2 ds equal to integral of rho v into dv. So it will be equal to integral of rho v into del x into dx. So from these equations, dn1 into ds minus dn2 into ds equal to rho v into del x into ds, where rho v is the volume charge density enclosed by the pillbox, so where del x is the height of the pillbox. So if the height del x is reduced to 0 across the boundary, that means del x equal to 0. So from this equation, dn1 into ds minus dn2 into ds equal to rho s. The normal component of flux density is discontinuous across the surface by the amount of surface charge density. So this it will be used for an electric field intensity E1 instant in the medium 1 at an angle of some angle declination, and E2 refracted in the electric field in the medium 2 with an angle of theta 2. Similarly, D1 instant electric displacement medium 1 and D2 refracted in electric displacement in medium 2. So the normal components of D is given by dN1 equal to D1 into cos theta 1, dN2 equal to D2 into cos theta 2. The tangential components E are given by Et1 equal to E1 into sin theta 1, Et2 equal to E2 into sin theta 2. So from these equations where theta 1 and theta 2 are instant angle and refracted angle respectively. So apply the boundary conditions. We already know dN1 equal to dN2, then Et1 equal to Et2. So d1 cos theta 1 equal to d2 cos theta 2. So E1 sin theta 1 equal to E2 sin theta 2. So dividing these equations, E1 by d1 into tan theta 1 equal to E2 by d2 into tan theta 2. So but we know that the relation between the d and e equal to epsilon into e. So therefore d1 equal to epsilon into e1 and d2 equal to epsilon 2 into e2. So from these considerations we have to obtain with that e1 by epsilon 1 into e1 into tan theta 1 equal to E2 by epsilon 2 into E2 into tan theta 2. So from this equation, tan theta 1 divided by epsilon 1 equal to tan theta 2 divided by epsilon 2. So from this equation, we have obtained with that tan theta 1 by tan theta 2 equal to epsilon 1 and epsilon 2. So this is the electric boundary conditions for electric field for between the two dielectrics media, that is called as an epsilon 1 and epsilon 2. So the final equation is tan theta 1 by tan theta 2 equal to epsilon 1 and epsilon 2.